We are in the fundamental concepts, the beginning part of the course, where discussed continuum hypothesis, the Lagrangian Euler approaches for describing flow, the substantial derivative following the fluid motion, and then the last lecture we discussed about different ways of visualizing the flow patterns in terms of streamlines, path lines and streak lines. Now we are at the end of the fundamental concepts, but two important topics, namely system and control volume. We will define them and distinguish them clearly, and then the Reynolds transport theorem, which is going to form the basis for the derivation of all the conservation equations. So, this is the outline. Of course, we start with distinguishing system and control volume. System has same meaning as in a thermodynamics course, exactly same meaning. Control volume could be any equipment, could be a heat exchanger, a distillation column, a reactor. And then the Reynolds transport theorem, we do it in steps. First, of course, we discuss the need for the Reynolds transport theorem. Next, we do the derivation in two steps. First, we derive a simplified form of the Reynolds transport theorem. We do a lot of assumptions and then get a simple expression. Once we understand that, we extend that to a more general form. To straight away derive the general form would be a little difficult, so we do it in steps. Okay, so let us start with defining and explaining what a system is, what a control volume is. This slide is for the system. In terms of nomenclature, system is also called as material volume. You will shortly see why is it called a material volume, but in terms of nomenclature, in terms of books, it is called as system or a material volume, both are equivalent. Now, how do you define a system? How do you imagine a system? As we have imagined a particle, how did we imagine a particle? We said the particle consists of large number of molecules and then we color it with the dye. Analogously here, we identify a set of fluid particles. There we identified a large number of molecules. The molecules constituted the fluid particle. Now we are going to identify a lot of fluid particles, and that is why you have a region in here. Okay. What is shown here is a material volume. What do I mean by that? At some time t, I inject a dye and color a portion of the fluid, which I call as system, and then I keep tracking what happens to these set of fluid particles and the same set of fluid particles. That is why I made it red and bold as well. That is the most distinguishing feature, or that is what defines a material volume. At time t, I color a set of fluid particles, let us say 100 fluid particles, and then what is shown here at some later time t plus delta t, let us say 1 second, let us say 1.1 second. This material volume has moved here. What is common between these two is the particles which are constituting the material volume or the system is same here. Based on the fluid flow, it has undergone some change in shape, etc. But to repeat again, made up of specific fluid particles, you color a set of fluid particles and keep tracking them and what happens to those set of fluid particles. As an entire region that may change in shape, etc., but we always keep focusing those, let us say 100 particles, always the same fluid particles. Okay. Now, of course, as I told you, the fluid particles are carried along the flow, and that is why there can be some change in shape, etc. Now, the way in which I describe this system or material volume is almost has the Lagrangian or material description. What did we do there? There we identified a fluid particle made up of large number of molecules, and then we followed that fluid particle. In this case, it is a large set of fluid particles, and then I keep tracking those set of fluid particles, and that is why it is a Lagrangian description or also called as material description. We said Lagrangian or material description, because we are following a material fluid particle, and that is why it is system is also called as material volume, because we are following a volume made up of fluid particles which are material fluid particles. So, can be familiar with both the terminology system and material volume. Most of the fluid mechanics books will use the terminology system. Okay. And of course, we are describing properties of a material volume. Okay. So, to just one significant definition or keyword from this slide is specific fluid particles, always the same fluid particles. We do not allow any fluid particle to enter, any fluid particle to leave. We always keep tracking the same set of fluid particles, no fluid particle enters, no fluid particle leaves, and which means that this system moves along with the fluid flow. That is why there is no particle entering, no particle leaving. So, the velocity of this material volume is same as the local fluid velocity. If it were different, what will happen? Some fluid particles will enter, some fluid particles will leave, and that is why the way in which I define a material volume, this velocity, all the local velocities, the velocity here, the velocity here should be same as the local fluid velocity. So, it just flows along with the fluid flow, and whatever happens to the fluid flow also happens to the material volume. Okay. So, let us demonstrate that this geometry is looks similar to our usual flow between two parallel plates, but with a difference. Here again we have two parallel plates, but in the earlier case both the plates were stationary, and a pump or external device made the fluid flow between the two parallel plates. But in this case this plate is stationary. Now, the top plate is given a constant velocity, and this movement of the top plate causes movement of fluid in the region between the two plates. So, the way in which we cause the motion of the fluid is different in both the cases. In the earlier case, some external pump made the fluid flow between the two plates. In this case, we impart momentum, we impart motion to the fluid in this region because of the movement of this plate. So, this plate is set in motion, that drags this layer, and so the entire fluid in this region is set in motion. Now, how does the velocity profile look like? The fluid here, let us say water, clings to the surface. When it clings to the surface, it has the same velocity of this plate, which is 0. Now, similarly, the layer of fluid here clings to that surface, and the top plate moves at the constant velocity. Because it clings to that, the fluid layer also moves at the same velocity as that of the plate. So, the velocity is here is 0, the velocity here is V p, and then after several lectures, several classes, we will derive this velocity profile or velocity field, but right now we will take it as a linear profile. So, velocity varies linearly from the bottom plate to the top plate. Okay. Of course, this velocity profile is required to understand what I am going to show now. So, to quickly summarize this geometry, we have two plates, the bottom plate is stationary, the top plate is given a constant velocity, and that sets the fluid inside between the two plates in motion, and the velocity profile is linear. Okay. Now, what I do at a particular instant of time, I select a region and then let us say color it with the red dye, and that is what is shown here at time t. So, whatever you color defines your system. So, in this case this region, rectangular region defined by A, B, C, D is your system. Now, because of the fluid being set in motion, let us see what happens to this system. Okay. Now, let me stop. What has happened now? First point, we said system is made up of a specific set of fluid particles. So, we have to focus only, let us say some 100 particles are there in this shaded region, we have to focus those 100 particles always. Now, those 100 particles are occupying a shape like this, let us say it is a parallelogram here, it was a rectangle here. Now, why is this happening? The fluid particles which are in contact with the bottom plate have the same velocity of the plate. So, they do not have any velocity at all, they are just stationary, and that is why they were never moved as time progressed as well. What happened to the fluid particles which were in contact with the top plate? They have the same velocity as that of the top plate. So, they are also moving along with the top plate, and that is why the system which had a rectangular configuration to begin with has become a parallelogram here, and something like my foot is held stationary as if my hand is alone being stretched, and of course, I completely deform. Of course, that is difficult to imagine, dangerous to imagine, but for a fluid it is fine. It is part of the fluid flow, depends on the fluid flow in the region. Okay. The point emphasized here is, once again, system is made up of the same fluid particles, and we track what is happening to those 100, let us say 100 fluid particles as time progresses. Okay. Let us take another example. This configuration is very well known to us. Just to quickly recap, we have two plates which are stationary. So, and then fluid is made to flow through this using a pump, and then the velocity is 0 here at this plate, the velocity is 0 at the top plate, and it is maximum at the central line. So, what should we know? The velocity increases from the bottom plate to the central line, of course, from this plate also it increases. Okay. Now, what is that I have shown here? Just like in the previous case, I have colored a portion of the fluid at some time t with a red dye, and that defines my system. And in this case, as the fluid flows, let us see what happens to the system. Once again, we focus on those 100 fluid particles only. Okay. Now, we are following those 100 fluid particles. Okay. What has happened now? These fluid particles which are nearer the wall have a lower velocity. These fluid particles which are near the center have a higher velocity. So, unlike the earlier case, in the earlier case the particles along AB were just stationary, and then along CD were alone moving because of the contact with the plate. But in this case, these particles are also moving, these particles are also moving. Of course, when I say those particles, all the particles in the system, they accordingly correspondingly move, and but these particles move at a slower velocity, these particles move at a faster rate, at a larger velocity, and hence once again to begin with we had a rectangle that has deformed to a parallelogram. Difference between the earlier and this case is both the layers keep moving, and but at different velocities. Earlier it was some 0 and non-zero velocity, but here two non-zero velocities, one is a lower velocity and another is a higher velocity. But the connecting point for all for both the demonstrations is that at a particular time we color a set of fluid particles, a larger region, and then we track and focus on what is happening to those set of 100 fluid particles, okay, and same fluid particles. Okay. Now, let us see what is a control volume. Okay. First, control volume is a geometric entity. Why is a geometric entity? Control volume is something you would have used very frequently in your process calculation course. For example, you would have taken a, let us say a mixing tank, and then two streams are mixed, and then you get a product stream, and then you would have drawn a dotted line around this mixing tank. That dotted line is nothing but a control volume. That is why it is a geometric entity. What is shown here is a control volume in terms of a dotted line, and then usually the control volume is stationary, it can be moving, we will look at examples, and then fluid flows through this control volume. Okay. So, let us look at that, a volume fixed in space through which fluid may flow. Why may flow? Sometimes it may be a batch condition, fluid may not flow, etc. That is why it says may flow. What I have shown here is a control volume, a geometric entity, because we have drawn a control volume to our convenience, and then fluid flows through this control volume. Now, as far as the fluid is concerned, its the sides are imaginary and completely invisible so far as the fluid flow is concerned. For our convenience, we have drawn a control volume here inside the region, inside the fluid flow region, and then here we have drawn a control volume around the mixing tank. So, it is for our convenience over which we write conservation equations. As far as the fluid flows, it is just imaginary and completely invisible. Now, this is the important point for control volume. Just like we had a key point for system, what is the key point for control volume? Fluid material inside a control volume is continually changing. What does it mean? You have fixed the control volume here. At this point of time t, some set of 100 particles or some set of particles are flowing through the control volume. Some other time t plus delta t, some other set of fluid particles are flowing through the control volume. That is why the fluid material inside the control volume is continually changing, in completely contrast to the system where the fluid particles which constitute the system were always same. That is a big and clear distinction between system and control volume. Fluid particles which make up a system are same, fluid particles which are inside a control volume keep changing. Some set of particles at this time, some set of fluid particles at some other later time. Okay. Now, the way in which I described, you can easily recall that this description is the Eulerian field description. Just want to recall, remember we had a chimney example. What did I say? I put a sensor here and then measure the temperature there, and then in terms of fluid particles, different fluid particles are being sensed by the temperature probe. So, we were at a particular point and different fluid particles passed through that particular point. Similarly, here also, instead of a point, we have a region here, we have region and different fluid particles pass through that region. Of course, it is along the Eulerian or field description describe the fluid particles inside the control volumes. Okay. So, to summarize this slide, the key point is fluid material inside the control volume keeps changing. That is the key definition of the control volume, and control volume is drawn or for our convenience, it could be drawn in a region like this, it could be drawn over a entire equipment like this. Wherever we want to describe the conservation, a region over which we want to describe the conservation, we draw a boundary. Okay. And of course, now it should be clear what is geometric entity. Geometric entity to distinguish from a material entity, which is material volume. That is why we distinguish that is a material volume, this is a geometric entity. Okay. Let us demonstrate the control volume. The configuration fluid flow between the two plates is known to us. So, let us straight go to the video. Let it pass once through the entire region, then we will different fluid enters and then crosses this region. Okay. Let the complete region be filled with the fluid particles, so that easy to So, now let us focus. I have shown two control volumes. The control volume is one control volume is shown inside the region between the two fixed plates, and as you see, you can of course easily imagine also by intuition different fluid particles. If I say, let us say I stop at this time, some set of fluid particles were flowing through that control volume, and then at some other time t plus delta t, some other time later, some other set of fluid particles are flowing through the control volume. Now, control volume can be over the entire equipment or entire region also. So, another choice for control volume is covering the two plates together. Now, fluid crosses this control volume, and fluid of course enters the control volume and leaves the control volume. Okay. Now, a terminology, the surface which surrounds the control volume is called the control surface. Okay. So, to be more precise, I should say that fluid enters the control volume through this control surface, and then fluid leaves the control volume through this control surface. Of course, fluid does not cross this control surface, it does not cross this control surface. If you recall back in your process calculation course, you would have had some mixing equipment and then you would have drawn a dotted boundary which represents control volume, and then when you do a mass balance, energy balance, you would consider streams which cross the boundary. Exactly here again, when I take this as my control volume, I consider only flows which cross the boundary, and what is happening is not considered. When I take this control volume, I focus on what is happening to the fluid flow in this control volume, which is the region inside the between the two plates. Okay. So, different forms of control volume are possible. Once again, what is to be understood is that fluid particles which are in the control volume keep changing with time, that is the bottom line. Okay. Let us look at control volumes in the experimental setups. The right hand side setup is something familiar to us, that is where we started the whole course in fact, and the left hand side setup is a new experimental setup. So, let us run the tank system. Just to recall, it is a small tank, it has two inlets and then one outlet. Water enters through both the inlets and leaves through the outlet. Now, I have shown different control volumes here. First, let us take this larger control volume. This larger control volume is around the entire tank. The inflow crosses the boundary here, another inflow crosses the boundary here, the outflow crosses the boundary here. This is exactly same as what you would have done in your process calculation course. Let me draw something similar to this, two inflows and then one outflow, and then you would have done taken a boundary and for writing a mass balance or energy balance. Only difference is that is a schematic and what you are seeing an actual experimental setup, that is the difference between these two. In fact, remember when we started the course, we said we will measure the two inlet flow rates and then calculate the exit flow rate by writing a mass balance. That mass balance was written around this control volume. Of course, I did not discuss about control volume etc., it was too early to discuss, but what is that indirectly we have done, we have taken this control volume and written a mass balance taking mass flows which cross these control surfaces. Now, I have shown few other control volumes. What is that? I can take a control volume inside the tank and analyze what is the fluid flowing through that, flowing in, flowing through out etc. So, my control volume need not be over the entire equipment and it can be inside the equipment. Remember I just mentioned about integral balance and differential balances. So, integral balances, of course, I will repeat this later again. For integral balances we take control volume over the entire equipment, for differential balances we take control volume inside the equipment. Now, I have shown few other control volumes. I can also analyze what is the fluid flow in the pipe which takes in water to the tank. Similarly, I have shown another control volume through which I can analyze the fluid flow in this pipe. Similarly, I have shown another control volume in the exit pipe. So, my control volume could be around the entire tank, it could be within the tank, it could be even in the tubes which lead the water to the tank or which takes water out of the tank. So, control volumes, the selection of control volume is based on our requirement, okay. Sometimes based on convenience as well, mostly based on requirement. Okay. Now, the setup shown here is a simple flow through a pipe, once again colored with ink for better visualization. What is shown here is a pipe, okay, and then it just water rises and then falls here. Okay. Now, my control volume, just like in this case, can be the entire region, the bigger red rectangle, and I can analyze the fluid flowing through, that is in this region. In this region, what is the fluid flow entering and then what is the fluid flow leaving and crossing the control surfaces, or as I have shown here, I can take a small control volume inside the pipe and analyze the fluid flowing in, out, etc. Okay. So, control volumes could be entire over the entire equipment, or it could be inside the equipment as well. So, in the earlier case it was a demonstration of a control volume. This slide shows control volume in actual experimental setups. Of course, you can extend this to equipments in industry and so on. Okay. Now, let us compare this system and control volume, taking an example, a very good nice example from this book Munson et al. Fundamentals of Fluid Mechanics. What is shown here is a fire extinguisher and filled with let us say CO2 gas. Now, the fire extinguisher valve is completely closed, and then at time t equal to 0, earlier it was t and t plus delta t, let us say 0 and some other time later, I color the entire gas inside the cylinder with some, let us say red color or whatever color, and define that as my system. Okay. What is my control volume? The cylinder is my control volume, and what is shown here, this dotted line, this dashed line represents the control surface. So, control surface is a boundary surrounding the control volume, and what is that we have done at time t equal to 0, we identified the contents of the control volume as the system, and this the entire cylinder as my control volume, and the control surface shows the boundary. Now, let us say at time t equal to 0, I open the valve of the cylinder. Now, what happens to my system? Part of the gas has escaped, the CO2 gas has escaped. So, now my system is still whatever the gas inside the cylinder plus whatever gas that has escaped. Why is that? We said moment we identify a system and it is constituted of set of, let us say in this case 1000 particles, I should always keep tracking those 1000 particles. The let us say about 800 particles are here and 200 particles escaped. So, my system still constitutes whatever gas inside the, let us say remaining gas inside the cylinder and whatever gas which has escaped. Now, what is the control volume? In this case the control volume remains the same control surface, the same control volume. So, this is a good example to distinguish what is a system, what is a control volume. We identified at time t equal to 0 a set of particles as a system, and we always keep tracking even though they have moved out of the control volume, but still my system includes whatever particles here and whatever particles here. In this case the cylinder is my control volume defined by the control surface. Okay. Now, what are the different possibilities for control volume? Shown 3 different possibilities. First case what we have is a flow through a pipe, and this dashed line represents the control surface. Now, a fluid flows in, flows out, etc. This control volume is fixed, the pipe usually does not move, you usually have a fixed pipe. So, the control volume is fixed and the surface of the pipe does not deform, it is rigid, and that is why it is a non-deforming and then fixed control volume. Fixed because it is stationary, it is non-deforming because the surface does not deform. Okay. Deform meaning change in shape, etc. Now, let us take the second case where our control volume is a engine in aircraft, a jet engine, okay, and then we want to analyze the fluid flow through this engine, let us say around the engine, etc. Now, this is my control surface which defines a control volume. In this case my control volume is moving because the jet aircraft is moving, jet engine is moving. So, my control volume also, you can't keep the control volume stationary, because otherwise if you keep it stationary your region of interest would not be there at all, it will be moving. So, you will have to use a moving control volume. What happens to the deformation? Of course, engines are non-deforming, it is very rigid. So, it is a moving and then non-deforming control volume. Here also non-deforming, here also non-deforming. Here the control volume was fixed in this case the control volume moves. Let us take the more general case. The example shown here is a balloon, a deflating balloon, which means that the air inside is escaping. So, and because air escapes, you know, the surface of the balloon cannot be rigid, it will start collapsing, and that is why it is a deforming control volume. And then if the balloon is deflating, it will go here and there, which means that the balloon also moves. You have a balloon completely filled, let us say you just start releasing air, you will just try to move here and there, and the surface will also start collapsing. That is why it is a deforming control volume, it also moves. So, the most general form of control volume is a moving control volume with a deforming surface. Okay. Of course, that is a most general case which becomes difficult for us to analyze. So, what is our scope? Our scope is the most simplest case, namely fixed control volume and non-deforming control volume. So, the entire course, all our control volumes will be fixed and will be non-deforming as well, okay, which is the most simplest case of control volume.